announcement, if you do need to get up and step out at any point during tonight's talk, if you wouldn't mind using the doors at the rear of the room, the restrooms are located just in the back by the elevator. So tonight is one of a series of presentations that HBO is putting on for Volcano Awareness Month. As you can see, there's a few more events remaining this month if you're interested in attending. All of them are open and free to the public, however the ones in the National Park might have park entrance fees. Tonight's talk is going to be by Cheryl Gansecki. She is a geology professor here at Hilo, and she specializes in the geochemistry of lavas. And tonight she's going to be discussing the 2022 Mauna Loa eruption and contrasting it with the lavas produced in the 2018 Kīlauea eruption. Cheryl has been instrumental in providing many research opportunities for students here at Hilo in processing and analyzing samples. And she's going to share some of her insight on what might be going on with these two volcanoes and their plumbing systems at depth. So with that, let's give Cheryl a warm welcome.
Thanks, Megan. Aloha. Good evening. So tonight, I would like to talk about tracking changes in magma over time, and between volcanoes and within volcanoes, how we do this, what we see, and what it means in terms of how the volcanoes behave underground and how perhaps they may behave once they erupt. So one of the driving reasons for giving this talk was that, so in 2018, there was a lot of talk that you may have heard and may remember about old magma and new magma up there. There's one of the Associated Press articles talking about the work we were doing at the time. But why didn't we hear anything like that with the Mauna Loa eruption? Right? That was a question that USGS was getting a lot. And so part of what I want to talk about today is why that's the case. So we'll start with kind of setting the stage. We have a map of the island, and our lava flows erupted in the past 1,000 years or so. And so Kīlauea, of course, as you probably mostly know, is this thing down here that's almost all red, completely repaving itself every 1,000 years. And then most of the rest of this is Mauna Loa, which is, of course, very active, has covered a lot of itself and a lot of the island also in the past 1,000 years. And a few little flows over there on Hawaii. So these volcanoes, they're some of the biggest and most active volcanoes in the world. They erupt a lot. There's a lot of magma coming through the system, erupting in a lot of different places. So there's a lot of opportunities for that magma to go through various changes. But I'll start taking a step even further back with what seems like a really obvious question, which is, what is magma, right? Something that seems obvious, right? If you ask someone what magma is, they'll maybe say it's molten rock, right? Or it's lava when it's underground. And that is true, or at least it's a start. Magma is a little more complicated than that. Magma is a silicate melt, right? Which is the molten rock made predominantly of silica and oxygen atoms that bind with each other and float around, binding with other elements down there. That's the molten rock part. But magmas also tend to carry crystals that grow in that magma. That's part of the magma as well, that grow in that melt. And also there are volatile elements or gases or fluids that may exist in this magma. So bubbles are another important part of magma. So that's all the things that make up a magma. So it's not just the melt. So when we're talking about a magma, there's a lot going on. Bubbles are important because that's what actually drives a lot of eruptions, right? It's those gas bubbles trying to escape, expanding, rising, carrying the magma with them. But for what we're talking about, the crystals are actually going to be important. So how can magma change? Right? If you have a magma, what's going to make it be different here or there or this day versus that day? And that turns out to be also a somewhat complicated question. We'll step even farther back and go back to Hawaiian Geology 101, which is why do we have magma in the first place? Hawaii is what's known as a hotspot, right? An area on Earth where we have an unusual location for volcanoes. Most volcanoes, of course, as you probably all know, happen where the tectonic plates of the Earth, this little shell on the outside, is broken into relatively solid chunks that move around, bump into each other. They tear apart on the seafloor and erupt volcanoes there. Spreading ridges, they also collide and one goes underneath the other one. They drag a lot of water down with them, which causes melting down in the mantle, and you get volcanoes above the trenches. So Japan, the Cascades, all around the Pacific Basin. That's where most volcanoes happen, on those edges of plates. Hawaii is a hotspot. All a hotspot really means is it doesn't fit the model for most volcanoes. The Hawaiian hotspot, not all hotspots are necessarily formed by the same process, but we know in Hawaii we have what's called a mantle plume underneath us. This giant column of hot, or at least less dense material that is rising from about 1,800 miles down beneath us, about the boundary between the core and mantle of the Earth, rises up. It's really, really hot rock, but it's under so much pressure that it's solid, but it flows. So it's kind of, we call it plastic material. It flows, but it's still solid. But as it rises up and gets close to the surface, the pressure is becoming less and less, can't hold it solid anymore, and it starts to melt. And once it melts, we have a liquid. The liquid is even less dense, so it rises even faster, erupts on the surface, and starts building a volcano. Of course, the plates are moving, right? They're moving around independent of the hotspot. So you build a volcano, it moves away, you build another one, moves away, because the Pacific plate is moving along to the northwest about the same rate your fingernails grow, about 4 inches a year. So that's why we have that nice long Hawaiian island chain. But so the magma that we're looking at is coming from this melting down there in the mantle at the top of this hotspot. So when we go to kind of decide, okay, when we're looking at changes in magma, there's a couple of different things that could be going on. One of them is going to be changes in the source. So down there where it's melting, something could be different. We could have, that the mantle might have variation, within that mantle material. There could be different amounts of melting. Sometimes maybe it melts more, sometimes it melts less. So there can be changes going on in the source as that melt forms and as it rises and begins interacting before it gets into the crust. And then once it gets up into the crust and into the volcano, then it starts getting stored and may begin to change in other ways that are a little bit more dramatic and more important for most of what we're talking about. The changes going on down here are mostly esoteric and subtle. The changes that can happen up here can be actually visibly seen. So we'll look at, there we go, what goes on in the magma once it's up inside the volcano. So some of the most important changes that happen in a magma can be all related back to one mineral. This is in Hawaiian magma. Olivine. Is everybody familiar with olivine, the little green crystal? If you live here, you've seen it for sure somewhere. If you've been to Green Sand Beach, you've seen a lot of it. Olivine is a really important mineral here because it starts growing at really high temperatures. It's a magnesium iron silicate mineral. And in Hawaii, they tend to be a lot more magnesium than iron. And it starts growing at really high temperature. So while that magma's down there inside the volcano, those crystals are growing. And that's going to affect the magma. How does it affect the magma? Well, we'll see how this works. There's a series of cartoons I put together about a magma chamber. So this is our funny-looking magma chamber over here. And it's full of elements, mostly silica, the little blue SIs. We've got magnesium and black here, so it's pretty abundant in magnesium. This is a typical composition of a pretty hot Hawaiian basalt with a little less than half silica, a lot of magnesium and iron and calcium, and just tiny amounts of mostly everything else. And so those are floating around in there, bonding with each other, but not really, at this point, making crystals. So what happens when it starts to cool is olivine crystals start to grow. So there's our olivine crystals growing, and what they're doing is they're taking silica and magnesium and little bits of iron and taking them out of the liquid. They're bonding with each other and they're forming crystals, so they're being removed So the more you grow these crystals, the more what's left behind is going to change. Olivine crystals are also very dense, so they have a tendency to sink once they form, or even while they're forming, and start to accumulate down at the bottom of the magma chamber. So you're removing that material from the magma. So this is how we can change the magma just while it's sitting there. You just start growing some crystals, and what's left behind ends up looking different. So now we've got a lot less magnesium in here, and everything, and there's a little bit less magma, and so now we've got a higher proportion of the things left behind. Something like potassium, this big K here, it's only small amounts of it, but the more and more you grow crystals, then it becomes, sort of by default, a higher proportion of what's left. The cool thing about olivine is that because these olivine crystals tend to grow very regularly as the temperature goes down, we can use it as what's called a geothermometer. So we can, let's tell you how this works. So this goes back to the 1959 Kīlauea lava lake. So you guys have all hiked Kīlauea, I hope, right? Got that beautiful flat floor that was once a lake of lava 400 feet deep. After it was cooling, the scientists at the time thought, wow, this is an amazing chance to actually study in place how a big body of magma, as it cools, does it actually crystallize in the way that we've been telling students for 50 years? It worked in the lab, but does it happen in reality? What actually goes on, right? So they were able to drill and get down into the liquid over time, so as it cooled and cooled and cooled, they could get samples of that liquid stuff, they could measure the temperature and see what it looked like. And what they found was you could make this beautiful curve here. All these points are the temperature that was measured, and then the percent of magnesium in the melt, in the glass, or the liquid part that was left, and found you could put a line through it and fit a little equation to it. And what that means is that with Kīlauea lavas, you can measure the weight percent of the magnesium in the liquid, in the glass, and you can calculate a temperature. So it's a little easier than trying to actually measure temperatures of big lava flows in the field, which is really hot and sometimes a little dangerous. So it's a very cool thing we can do, and so that's one of the ways we can use the chemistry to help us figure out how the volcano is going to behave. So once it cools a little bit more, you start growing 2 other crystals, where we only basically have three crystals that you can see in Hawaii. The white ones, the plagioclase feldspars, and clinopyroxene, which it's pretty rare to actually see. It's a black, usually a little black mineral. Those will start taking out calcium as well as magnesium and iron and silica. And so you can actually do the same thing with calcium as it gets left behind. If those crystals are present, then we know this one works as well. But the more you grow the crystals, then what's left becomes a higher and higher proportion. So here's our starting magma at high temperature. As it cools and you remove crystals, you have less, so the pie is smaller, right? But also you notice our proportion of magnesium has shrunk a lot, iron and calcium as well. But the relative proportion of things like potassium and those trace elements, the ones that are kind of floating in there but don't actually fit into any crystal structure, so they just kind of get left behind, they get larger proportions too. So these are some of the key elements that we use when we're trying to fingerprint what the magma is doing. We look at magnesium, we look at potassium, we look at zirconium as kind of one of these elements that really doesn't like to go into any crystals that grow in basalt, so it's always going to be left behind. We call it an incompatible element. It's just not compatible. So we've got that background. Now, in order to actually do it, you need to get some samples, right? And in order to measure the composition of the glass, you have to quench the lava. Either it quenches itself by erupting into the air as spatter or something and falling down and cooling into glass in the air, or you gotta yank a piece out and try to get it into water or something to cool it off quickly so it doesn't have a chance to grow and then change its composition. So here's some sampling from 2018 of flows of the lava river and from a spatter rampart. Okay, once we get the samples, then what do? Well, if they're wet, which they often tend to be, especially if you pour water on them, or you live in Hawaii where it rains all the time, the samples have to be dry. They have to be analyzed, they have to be prepared, and then you run them on the EDXRF lab. So this is a lab run by Steve Lundblad and Peter Mills. It's an instrument that we've had here for about more than a decade now. And the unique thing about it is, so most geochemistry is done long after the eruption is over. You get the samples, you send them off to a lab, they get in a line, they wait for months until there's time on the very expensive machine, and eventually, 6 months later, you get some data back. With this, we can get data within just a few hours, or if we have to dry the samples, then generally within a day. So what that means is that this chemical data that we get can be not just something that goes into a paper 3 years later, it can actually be part of the monitoring. So we can get that data back to the observatory, and they can see any changes going on while it's still erupting and still in time for it to potentially be useful. And of course, this is the current student, Bailey, who is working on the project. She was amazing in the Mauna Loa eruption, just jumped right in and spent a huge amount of time running samples. Okay, so how does our magma change over time then? I've kind of given you the background for ways it could potentially change. How does it change? Well, thinking about those two different ways that magma can change, right? Our source versus our crystallizing and things that happen when it starts cooling. This is a diagram over about 45 years of Kīlauea eruptions. And what I'm looking at here is the more subtle changes that may be related to the source. So what we've done is corrected the data so that it's essentially corrected all to the same temperature, so that if any sort of extra olivines are in there or removed, it corrects for them. So what we're seeing then, so this is potassium over time. So back over here on the far left is summit eruptions from 1982. The black triangles are āweoweo eruption from 1983 all the way to 2018. And then up in here, 2018, and then in purple is this current summit eruptions that have been going on Kīlauea. And what we see is that while there's some variability, there's definitely some subtle trends. So we can see there's a little jump between 82 and 83 or 84, where āweoweo started off with pretty high potassium, and then over kind of the next 2 decades, the value went slowly down, kind of bottomed out in 2000 and stayed about the same for another 15 years or so. And then just starting around 2016, it started to rise again. And then with 2018 and the current eruptions, it's still staying up there. So this seems to be a fingerprint of some change going on in the source that's feeding Kīlauea. Not necessarily something that's happening during, related to the individual magma bodies. But it's subtle, right? We're talking about a 0.1% change at most. So there are subtle differences. That kind of difference isn't really going to affect us, as people living on the volcano. That's more just of interest to geochemists and people that study the volcano and the hotspot. Now, Mauna Loa, let's see if we can look at something similar for Mauna Loa. We don't have as much data, right, because it only erupts for a while, every 5 years, and then now it's kind of spread out. We can see also some subtle changes in this is a ratio of elements that shouldn't really change much. And we see some subtle changes back in the 1800s, where it was going down, and then it kind of came back up, and then since about 1942, it's stayed basically about the same. So seems like the ultimate source of Mauna Loa is not really changing very much. Possibly some subtle changes around 1868 or so when we had the giant earthquake and eruptions there. Okay, so that's the source. Interesting, but okay, not really necessarily going to affect us so much. Let's take a look now at what's going on during individual eruptions. So that's Kīlauea. Kīlauea, of course, had a āweoweo eruption starting in 83, kind of out there in the middle of the rip zone. This is a very simplified cartoon of the inside of the shield volcano, Kīlauea, with the Pu'u'o eruption out in here in the middle of the rift zone. Starting in 2008, a summit eruption up in here. And so those eruptions were going on. And then in 2018, right, it erupted down here at the lower East Rift Zone, kind of way down low, drained magma out from the summit, caused the collapse. And then, of course, since 2020, we've had lava go back up in there. So it's been very, very active, and a lot of different eruptions. So what was the chemistry doing? The volcano was certainly doing lots sorts of fun stuff, right? We've got fountains and fissures and lava tubes and lava lakes and various lava flows. What was the chemistry doing? So Pu'u'o, our project actually started in 2012. So we can certainly look at other data, but with our instrument we try to keep it all consistent. So from 2012 to 2018, the Pu'u'o lava stayed really very, very much the same. It got a little bit boring after 5 years of looking at the kind of the same stuff all the time. And so what we're looking at here is a plot of magnesium on this side. So we can see it's kind of in the high 6s to 7.5 or so weight percent, very typical. The zirconium is what we're going to be looking at, kind of in a minimal range, kind of around 145 or so. And then over here, we're going to look at the temperature. So this is using calcium. You could also use magnesium. But for Pu'u'o, kind of up there around 1150 or so during that time. So limited range, not a lot of changes. It was a little dull, to be honest, after a few years. Then we had 2018. And so the very first eruption of 2018, we saw these yellow points here. So big change, right? In that first week of the eruption, we saw a much lower magnesium right down there at 5 weight percent, which puts us down there like 1110, so 40 degrees cooler than the normal lava we've been looking at. And at zirconium levels, more than double what they had been. So this is kind of almost the highest we'd ever actually seen on Kīlauea at the time. So it was not a surprise, because we knew that Kīlauea does have a tendency to, when magma does come through and erupt down there low on the volcano, it does tend to find old stuff and push it out. And that seems to be exactly what's happening here, is it found some old lava that had been sitting there, cooling, crystallizing, pushed it out. Okay. Had a little break, lava started up again. This time, when we analyzed it, we saw, it's hotter, right? It's gone up a little bit higher temperature, lower zirconium, higher magnesium. So not really the full lava. We know that's not lava coming from the summit, but it might be starting to mix with our stored lava now. And this is at the point that we realize, okay, the hotter stuff is coming, the lava is going to start to behave a little bit differently. Because when it's cold, it tends to be kind of stiff, doesn't move as easily, and flows slower. Then we had fissure 17, which I suppose everybody remembers, that crazy thing, where all of a sudden we were getting these values way up where we've never had them before. Really cold, stiff, explosive lava coming out of the ground. I don't know if you remember, the first analyses we got back, I was like, that can't be right, go do it again. There's something wrong with the machine. And then finally we realized, wow, it really is this different. Something completely different, really amazing. Something that had been stored for a long time but was still liquid enough to actually get pushed out of the ground. And then starting around May 18th, the hot stuff arrived for sure, and that's what was known as phase 2 of the eruption. Lava flows suddenly increased in volume, moving fast, going to the south because they were erupting from some fissures that were basically open to the south. So big flows, a little more destructive, got to the ocean in a day or two, and so we're seeing now they're getting back up to Pu'u'o type temperatures and compositions, much hotter, higher magnesium compositions, and bottoming out on our zirconium, so our incompatible element there. And And then starting May 28th, of course, the whole Fissure 8 thing got restarted, a giant river of lava that just took out Poho and all that stuff along the coast. Basically for the rest of the eruption, it pretty much stayed very similar after that. So we have the zirconium didn't really change, magnesium that had a lot more variety, but we think that's related to basically picking up olivine crystals as it went, because olivine, remember, is carrying all this extra magnesium, so once you analyze the rock, if it's got too many olivines in it, suddenly it looks like really high magnesium. So we used the calcium for the temperature, and it showed us it pretty much just leveled out. And that's a pretty typical temperature for a magma that traveled 25 miles down the rift zone to get there. Okay, so here's just the map. To just recall, so the initial eruption is the yellow lava, just these little tiny fissures, except 8 was a little bit bigger. That first week, and then the green, kind of the second week, and black are the actual fissures as mapped. Fissure 17 up here in red, and then the blue for phase 2, and then of course the final map with the big blue being the phase 3, the big hot flows, and various numbers of the fissures there. So a lot of very distinct compositions. So what's interesting is when we're talking about kind of effects on, say, how the lava moves or how it works, there's kind of two, depending on how much you actually crystallize this, will affect how it behaves. So if you crystallize it to some extent, it's going to get a little more viscous, and generally what that means is the flows are going to be a little stiffer, maybe more likely to be an on-off flow. They may not move as fast, and so generally they're going to be slower. So in terms of like hazard, that tends to decrease the hazard a bit. They're not going to flow as fast. It's a little easier to get out of the way. On the other hand, if you get to extreme crystallization, like with the Fissure 17, you start getting so viscous, and what also happens is that the gas begins to accumulate, because things like water, which is dissolved in the melt, as you crystallize, it doesn't go into the crystals, right? They're not wet crystals, so it gets left behind too. So if you crystallize it enough, it starts building up those volatiles, those gases. So the combination of a lot of gas and a really stiff magma means that the bubbles, once they form, can't expand very well. They build up a lot of pressure, and so they tend to explode rather than just bubbling to the surface. So it becomes more explosive. So you go from, okay, you let it crystallize to some extent, it's maybe a little bit less hazardous. Too much, and it becomes a little bit more hazardous. And of course, you all may remember Fissure 17, just for fun, I thought I'd put the video in. So you can see, this is Fissure 17. This segment was mixing with a little bit of more fluid stuff. This was the explosive end with the full-on andesite. So you're getting these really gas-rich, pulsing explosions from the ground. It was more intimidating. We had about 7 kilometers, about 4 miles of fissures, which was pretty good, pretty long. Eruption lasted 3 months in total. The eruption rate, at least once the channel got going, kind of around 150 cubic meters a second. What does that mean? We can use Ken's dump truck analogy. You think about those really large dump trucks that they use to bring gravel or mines. It's about about 10 of those a second? Yeah, about 200 cubic yards a second. So So a lot, right? A pretty good amount of material moving, but a cubic kilometer of lava erupted. So very, very large eruption. The variability in the chemistry, very high. Pretty much the most extreme we've actually seen on Kīlauea. But, so the question becomes, okay, well, why is that? Why is it so variable? There have certainly been other eruptions that were just as big, but they didn't have the same variability, or at least quite so extreme. And so this is kind of a slice through Kīlauea volcano, at least my version of it, at least in 2018. One thing we knew is that under the summit of Kīlauea, the magma system actually has two magma chambers, two magma reservoirs, a shallow, smaller one, and then a deeper, larger one. And when it erupted down here and drained, it actually drained mostly the smaller one. That's what caused the collapse up at the park at the summit. But so it had been erupting here at Pu'u'o, was blocked from going any further down the rift zone up until then. And then when that broke open, the magma moved down, and it was flowing at about somewhere between 3 and 4 kilometers depth. We could see the earthquakes down there, so we knew it was down at that depth. And then it rose up through into the shallow and then erupted at the surface. And that's in here where it presumably met some older stored magmas. Most likely, at least 1955. We know 1955 lava erupted right through Leilani Estates. It didn't exist at the time, but it did a few years later. But also there had been eruptions down there, 1960 a little further down, 1790 right through the same area, 1840 kind of on the north side. So there had been other eruptions, but still relatively infrequent enough that they don't flush each other out that frequent, that often. So they have a chance to get stuck, basically. And part of it is that when you're erupting down here, a lot of the driving force for the eruptions is gravity. So it's basically flowing down and being driven as this is going down, this is flowing out, it's got some head on it. And then finally, when it kind of reaches equilibrium, there's no more pressure to drive the eruption and it just stops. But the whole thing in between is still full of magma, right? So every eruption leaves a lot of magma behind inside the volcano. It's kind of like the shower in the morning, right? It was nice and hot the night before, but when you turn it on in the morning, it's cold until the hot water gets there. So kind of the same thing with our plumbing system here. So we think there's pockets of this magma deep enough to stay hot for decades, maybe even a century or two. There's some debate between various geochemists and other scientists deciding, how long they think that stuff can actually survive down there. But at least, definitely for decades. So this eruption hit one and possibly two different magma bodies between the first lava and the andesite, the Fissure 17 stuff. So that's partly why this particular eruption was so variable, because it happened to hit of older magma. Okay, so Mauna Loa. What happened with Mauna Loa? There's Mauna Loa. Takes up a big chunk of the island. It has a summit caldera, Moku āweoweo, kind of an area that encompasses the crater and some of the smaller craters around it. It's also got some rift zones, right? It's got a northeast and a southwest rift zone, kind of roughly outlined by those lines. And it also has a tendency to occasionally erupt on its north flank. It kind of gets stretched and pops out what we call radial fissures off from this north side occasionally, but not as often. Usually, all Mauna Loa eruptions start at the summit, so it erupts up there, and then it either stops, or it goes to the east, or it goes to the southwest. That's the pattern we've seen in all the historic eruptions. So, and it's kind of goes back and forth. You never know which one it's going to do. Okay, November 27th, 11:20. Well, before 11:21, right? We got the call, and we were. 11:21, the volcano started erupting. This is a picture we took as we were going over. This is from Kona, looking up at Mauna Loa. It was already erupting, already starting to fill the crater. At this point, we didn't know which way it was going to go. We knew it was in the summit. We didn't know which way it was going to go, and that was pins and needles, because there's a huge difference between whether it goes to the east or whether it goes to the southwest in terms of the hazards, right? Probably everybody knows this, but if it goes to the east, right, it's either going to kind of pool there in the saddle or make its way towards Hilo eventually, but that takes months. If it goes to the southwest, we know it can go ripping through and go from 10,000 feet to the ocean in 3 hours. So there's a huge difference in hazard. So that night was really, really worrisome for all of us. And from that view, you could see it did look like it might be on the southwest, but the webcams on the southwest Rift Zone weren't showing anything moving down. So that was at least a relief. And so what we found out is that basically the caldera ripped open. So this is Mauna Loa over here. This is the caldera area. So it ripped open through the crater and then a little bit to the southwest, but didn't actually go into the rift zone. But it did send some lava flows down the upper part of that side, which is why people in Kona and down the south were freaking out for good reason. But luckily it didn't go any further that way, and in fact it promptly started heading off to the east. This is the next day. So this is, if we're looking from the southwest towards the crater, this is the new stuff. You can still, it's still fuming a little bit, some little flows that came off, but already the activity has moved to the east. And so here's just, it pretty much quickly ripped open fissures 1 and 2, and then fissure 3. By the next morning, all of this was stopped at the summit, and really by like 1 o'clock that evening, or that day, the first 2 fissures stopped, and 3 became the most active location, and 4 popped open as well. It was active for a while, but never quite as large as fissure 3, which became the main vent. So here's kind of a whole bunch of those channels in the early days, big flows coming down. Of course, hopefully everybody got to see these spectacular channels from the saddle or somewhere. So, let's see. So here's just a couple of videos from, this was the first morning, so we were up in the C-130, so we're kind of looking through a tiny window, it's a little awkward, but you can see those fissures, and the big flow is already starting mostly to the east-northeast, coming around. This whole thing is still active fissure, there's another one back there. So the fountaining, generally going sort of 50 to 100 feet high, sometimes up to about 200 feet. And yeah, here's on the HVO folks on the ground, looking at this just gorgeous spattering along fissure, kind of classic spatter ramparts that have started to pile up along the edges. And feeding good-sized flows. Here's a couple days later. So kind of a nice wide-angle view of the fissures, and then some of those flows coming off and heading now to the north, starting to advance towards the Saddle Road. And a couple of little active fissures, still just barely active, but still feeding some flows at that point before they shut down. Eventually, by December 4th, they started building a big spatter cone up at the vent. So the fissure 3 vent became the main center of activity. Some good-sized lava rivers feeding the flow. You can see the lava, the channel is pretty smooth, and it's very strong. So it's carrying lava balls, so pieces of lava channel or cone that fall in and get essentially rafted along. But the front of the flow and the sides was so the channel could be more fluid, but out at the front, this is what the flow looked like. So kind of a 15 to 30 foot high flow, liquid on the inside. This is pretty much, I think, where it crossed the Hilo Kona Road, the easiest place to access. And so it's just slowly kind of spreading a little bit at the sides, and most of the activity was at the front. So it slowed down once it hit the flats, luckily, and started spreading, and then, of course, never reached the highway, thank goodness. So sampling in Mauna Loa is a little bit scarier than sampling had used to be. It used to be. Certainly in Pu'o days it was pretty easy. 2018 was tricky. Mauna Loa is always a little bit, everything's always a little bit bigger on Mauna Loa. But here's our master geologist and sampler, Frank Truesdell, collecting samples. First of all, spatter. So trying to get fresh lava. So waiting for it to come flying out, grab it, and then run out. And then, so he's dumping it in a bucket, and then gonna try to get out of there. And then we need to pour some water on it to quench it. Just kind of trying to break it up a little bit so water gets to the inside. Well, they're also keeping an eye on the cone, of course, because it could be sending stuff flying at you. Definitely want to watch it for a while before you try to approach it. The other reason to cool it, of course, is the fact that if you put it in a bag, it's going to melt the bag. So you gotta wait for it to get cool enough. So, they definitely melted the first bag. Now here, Frank is going to get a sample from a lava river, which is also terrifying. So the lava, you may be able to tell from this image that the lava around the lava channel tends to be what we call very shelly lava, so a lot of hollow, easy to collapse space. So it's very kind of fragile, and you have to approach it very carefully. Frank is definitely the most experienced of anybody at HVO at sampling. And so he's going to go get a sample from the lava river. So he's wearing a heat protective jacket. Trying to cover every bit of exposed skin. Some kind of head protection on the approach very, very carefully. So you don't want to step on anything thin. Just found a little rock to kind of shelter from the heat a little bit.
Yay! I'm still alive.
You made it! And then, of course, you need to record the time that you took the sample and the location, so we know exactly where and when it formed when it gets back to the lab. So, okay, what did we learn? I'll go through a series of geochemical data, very exciting. Again, we're looking at magnesium and zirconium again, so very similar to what we looked at before. Only this time we'll just watch what happens over time. So these are samples from the summit, right, the first part of the eruption. And we see, okay, it's pretty limited range, about 6.5%, a little bit less magnesium, so a little bit cooler than most eruptions up there, but not too different. The zirconium, a little bit higher, kind of around 145 to 150. And then we start looking at samples collected over the next few days. So the different symbols are the different fissures, so fissures 1 and 2, fissure 4, the blue is fissure 3, like that real active one. And what we see is nothing, really, right? Basically with thin air, it's all pretty much exactly the same. And all the way to the end of the eruption, it's pretty much exactly the same. So, very different than what we saw. If we compare it with the historic data from Mauna Loa, so over here is like the history of the different eruptions up till the most recent. So here's the most recent zirconium. See, it's actually quite a bit higher in zirconium than previous eruptions, or similar to way back in 1843. Whereas the magnesium also very low, but not anything too low compared to some of the others that we're looking at. In blue are the East Rift Zone samples, red are Southwest Rift Zone, and then there's one little north one from 1859. But otherwise, our magnesium fit in here, looking like, okay, maybe this magma crystallized a little bit, but it's definitely not hitting anything old. So what we had in Mauna Loa was 17 kilometers of fissures instead of 7. So much larger area got ripped open and lava erupted from it. The eruption only lasted 2 weeks though. The eruption was very similar, pretty much the same as the kind of the high rate in 2018. About a quarter of the amount of lava erupted because it's a shorter eruption. But the variability, really, really low, right? It hardly changed at all. So what does it mean? Why? And I think it has to do with the fact that the plumbing system inside Mauna Loa volcano is different. It doesn't erupt as often, and what it does tend to do is once the magma moves up, it tends to stay pretty shallow. So in our first part of the eruption, the dike, the lava magma intruded up, erupted at the summit and a little bit down the side, kind of within the caldera, and then ripped off to the northeast, but it stayed very shallow. Basically, you could see where it ripped right across the surface. So it's not going very deep. And so it's not got a chance to hit anything that's been stored, because everything close to the surface is going to cool faster. And if it's solid, it's not going to mix with the liquid. It's just going to break open, cut through it. So you don't have a chance to really encounter these older magmas. Also, of course, the volcano's a lot bigger, so the chances of hitting something are smaller. But I think a lot of it just has to do with this difference in plumbing. Kīlauea, when it goes down the rift zone, sometimes goes deep and then comes back out somewhere way down below. In this case, everything stayed pretty high up on the volcano. That vent was up at almost 12,000 feet. So it didn't come very far down. So it was staying pretty high on the volcano. So those kind of the big differences between the two. I would like to thank all the people that have been involved in this project for a decade or more. Students, we've got my colleagues in the lab, my USGS colleagues. There's Kendra and Drew, the new geologists that now work a lot on the geochemistry as well, and all sorts of folks who have worked over the years. So aloha and thank you. If you want to see some Mauna Loa samples, I have some of the tephra, so the loose, fluffy stuff that was thrown up in the air and landing around the cone, and then also a couple of those samples that Frank collected where he kind of pulled it out and cooled it so you can see what they look like when we get them back to the lab. But before that, does anyone have any questions?
I'm just going to ask, you're going to say you don't know, but is Pu'uo'o maybe extinct?
Pu'uo'o is probably extinct. I mean, I don't know for sure, but it seems to be pretty dead at the moment, anyway. Yes.
Have you guys done any modeling trying to figure out how long it takes for those zirconium or incompatible elements to increase that much when the lava is stored? I saw that Mauna Loa was significantly higher than the 20.
Yes, I meant to talk about that actually a little bit. In that is something I meant to mention, that because the magnesium was low, the zirconium was high. I think it's possible that, we know Mauna Loa has been pumping up, particularly in the last decade. We see it kind of expand in the earthquakes, and then it would kind of taper off and expand again. So magma's been moving in, and it's possible that it's been in there long enough, a decade or so, enough for it to cool a little bit, crystallize a little bit. There has been modeling done about that, but yeah, there's a lot of arguments about it too. But I think that's quite possible, that the part of the reason that it is higher is because there was such a long gap, and possibly the magma was moving in. But the amazing thing is how homogeneous it was, that for over 17 kilometers, it was exactly the same magma, all the way from one end to the other for 2 weeks, which suggests also that that magma body down there is pretty well mixed, right? It's not zoned, it's not going to come out one and change over time. It's definitely mixed. It's all pretty much exactly the same stuff, which is pretty cool. Yeah.
So you said that with this most recent eruption, there wasn't a lot of variability geochemically because the magma source was really pretty shallow when it was traveling along the fissures. But then historically, there's a lot of variation, and then obviously a lot of the fissures and vents and things have been at different elevations because of the significant height of the volcano. So do you think that any of that variability throughout history could be because the lava or the magma is actually traveling like lower elevation-wise through the edifice of the volcano?
Yes, exactly. Actually, and the 1868 eruption, so basically any eruptions that are really down low on Mauna Loa tend to be really different, because what happens is, remember we were talking about how olivine is dense and heavy? It sinks down, and so it accumulates deep in the volcano. So when the volcano gets ripped open on its low end, so Green Sand Beach, for example, when the magma comes down through there, it has a tendency to scoop up a lot of that settled out olivine and push it out. So the chemistry comes out really different, right? Just really high in magnesium, because it's just chock full of olivine. If you've been out to Kahuku, you've done that walk out there, that stuff is all full of olivine. If you go out to Green Sand Beach, not just the beach, but all the lava out there, which is all coming out really low on Mauna Loa, just full, like 30% olivine in the rock. So that's because it's coming down low through the volcano and scooping out a lot of its deep guts, I don't know, whatever the stuff that's settled down deep in the volcano.
So do you think any of that could be older, like how you mentioned with Kīlauea, there were old magma pockets?
No, not in the way that we see on Kīlauea, because it's kind of the opposite. It's more, it hasn't sat there cooling and crystallizing. It's hot, deep stuff that's kind of just stuck inside the volcano. But I mean, it's possible, but we don't really see any of that really extreme variability that we see on Kīlauea on Mauna Loa. At least not that I know of. I haven't seen it. Not historically, anyway, yeah. Anyone else? Well, thank you guys very much. Aloha. Enjoy the rest of the talks and Volcano Awareness Month. Aloha.